So now that we've talked about how to implement a custom structured task scope, let's take a look at a case study that will demonstrate in more detail how to implement a custom structured task scope and also how to apply it. And this particular example can be found in the ex5 project in the Loom folder in my live lessons GitHub repository. And here we are in the ex5 project in my Loom folder in my GitHub live lessons repository, and this is the example we're going to look at. So this particular example is going to show how to create and use a custom structured task scope that will capture the result of the first subtask to complete successfully, namely to identify a prime number without returning a null. And of course, you have to use modern Java to make all this stuff work. So here is the program. We're going to have a list of large numbers. I could have had a random number generator, but I wanted to have complete control over the numbers here. And some of these numbers are prime, some of these numbers are not. There's actually a program on the line where it'll generate for you as many prime numbers with as much resolution as you want. And of course, you have to be careful not to have too much resolution because it'll overflow the size of a long. But this worked just perfectly. So here's the test program. We're going to demonstrate custom structured task scope. And here's the program. So you can see we're going to make a new scope, which is going to be our shutdown on non-null success class, which we're going to look at in a second. And so that class is going to provide the semantics where it'll only return a result when we get a successful, i.e. non-null result. And it's parameterized by the return value, which in this case is long. So we're going to make ourselves a new scope. That should be very familiar to you now that you've been working with Java structured concurrency and structured task scope for a while. We then take that list of numbers, and for each number, we're going to go ahead and fork off a new task. And this task, of course, will run as a thread, virtual thread. And we're going to call the isPrime method, and we'll see what isPrime does. It returns 0 if the number's prime. Otherwise, it returns the smallest factor for the number. And if we get back a 0, that meant it was a prime number, so we return the number. Otherwise, we return null. Maybe the word return, I should say yield. It'll yield the number. And remember, this is passed as a lambda expression into fork. And therefore, one of these two numbers will be the results of carrying out this computation in parallel with all the other virtual threads that we have running around. And we'll take a look at how this shutdown on non-null success custom structured task scope works in a second. So all these guys are up and running. We call join, and this will only return if we get a successful computation, or we don't get anything. None of them are prime, then it's going to return as well. When we're done, we get the result by calling scope result. That was mimicked, modeled explicitly and intentionally on the way you work with shutdown on success. And if we get back a non-null, then we print the result. Otherwise, we say no prime numbers were found. So that's the driver program. Now let's go take a look at a couple things. Here's the prime utils method. Here's the isPrime method. Sorry, prime utils utility class and the isPrime method. And all this is doing is it's just burning up some CPU cycles, trying to determine if the number is prime or not, and if it's not prime, what its smallest factor is. And you can read the comments if you want to learn how this works. It's intentionally not the most efficient way of doing things, but it's not ridiculously inefficient. And again, it's just there to burn CPU time to make the program interesting. Here is the shutdown on non-null success class. And you can see here that this extends structured task scope. It defines a volatile field called mResult of type T. T is the parameter that's passed in here. We use volatile because, as we'll see, there's a call made internally here, which is called handle complete. And that call can be called by multiple threads simultaneously. So we want to be able to atomically read and write these results. Shutdown on non-null success is the constructor. We're going to make an unnamed structured task scope that will create virtual threads. So that's what that's doing. We're saying make virtual threads, please. So we give it the virtual threads factory. And then here's the workhorse method in this class. This is called handle complete. As you can see, this is overridden from the superclass, and it's passed in a completed task. So what's happening is the framework itself, the StructuredTaskScope framework, is off running all these forked tasks, and each time they complete, the handle complete method is called back. Now, normally, you'll use whatever the default is, and we'll take a look in a second at the default implementation of this stuff, and also the implementations for shutdown on success and shutdown on failure. But our case wants to handle this method explicitly. So we subclass from StructuredTaskScope, and we override the handle complete method. And what we do here is we check to see what the state of the future was. So when the future completed, or the framework thought the future completed, it passes the future, and we can then go ask the future, what is your state? And if the future state is running, then, oh my God, something horrible has happened. I'm not even sure how we got here, but we throw an illegal argument exception saying, hey, this task wasn't complete. It wasn't shut down after all, or wasn't complete after all. If it completed successfully, then we're going to go ahead and grab the state. And in fact, I should probably just say, since I've already done this, I should probably just say if state equal future state success. Don't have to wrap that up because I already recorded it here. Then what we're going to do is we're going to get the result of the future. Now notice that this future, there will only be one thread accessing this future's results because it's passed as a parameter. So we don't have to worry about the call to t result equal future dot result now being incurring race conditions or requiring any more synchronization. That code will never have to worry about anybody else competing with that value. So we stash the result here of whatever the future had. And then we check to see if the result is null or not. If the result is null, then it was an invalid result. It was like we checked is prime. It wasn't prime, so we want to ignore it. So you can view null here as basically ignore me, please. And so if it's null, we're going to ignore it. If it's not null, that means that this was the first one in. This was the very first value we got back. And in that case, we're going to set mResult equal to result. And that call needs to be atomic. The assignment here needs to be atomic, which is why we made the mResult volatile. And we're then going to go ahead and shut down the scope. And when we call shut down, that's a call into the framework, into the Java framework that handles this stuff. And that will kill off all the other virtual threads and allow join to return. So when join returns at this point, it's going to end up calling result, and result just returns the mResult value that it got assigned when the first non-null future completed, when the task associated with the first non-null future completed. And then at that point, we can go ahead and grab that result. So that's the end of the overview of this example. This will give you a much better understanding of how to write custom implementations of StructuredTaskScope.